equations for undergraduate students. Today's lecture is on the solution of second order partial differential equations. In last lecture, we had learned about the second order partial differential equations. We have classified those equations and changed them to the normal form. Now, we will go for the solution of second order partial differential equations. First, we will stick to the linear second order partial differential equation, they are which are homogeneous one. So, as in the case of second order ordinary differential equations which are homogeneous, here also the superposition principle holds, that is the first result which holds is, that is fundamental theorem. So, the result says is superposition or linearity principle. The result is, if u1 and u2 are any two solutions of linear homogeneous partial differential equations in some region R, then a linear combination U as C1 u1 plus C2 u2 with any constant C1 and C2 is also the solution of that equation in that region R. For being a solution of any differential equation, we do know that the function must have the second order derivatives which are coming in that equation, and it should satisfy that equation. So, using this is the first result which is holding true. Let us just try to see certain second order partial differential equations which can be solved as linear ordinary differential equations. Before that, let us come to the proof of this fundamental theorem. This is a very simple one. Let a general homogeneous linear equation of second order be a times del 2 u over del x 2 plus b times del 2 u over del x del t plus c times del 2 u over del t 2 plus d times del u over del x plus e times del u over del t plus f u is equal to 0. So, we have taken completely linear second order partial differential equation. If u1 and u2 are two solutions of this equation, that says they must satisfy this equation, that says is I should get a times del 2 u over del 2 u 1 over del x plus b times del 2 u over del x over del t plus c times del 2 u 1 over del t 2 plus del 2 u d times del u 1 over del x plus e times del u over del t plus f u 1 is equal to 0. Similarly, for u 2 also the function u 2 must also satisfy the equation. Now, we have to show that its linear combination C times u 1 plus C 2 times u 2 is also a solution, that is now I am taking u to be as C 1 u 1 plus C 2 u 2. That says is if I put this function in our differential equation, we would get the second derivative with respect to the variable x of C 1 u 1 plus C 2 u 2, the second derivative with respect to x and t as C 1 u 1 plus C 2 u 2 and so on, the second derivative with respect to the t C 1 u 1 of C 2 u 2 and the first derivative with respect to x of the function C 1 u 1 plus C 2 u 2 and the first derivative with respect to t of C 1 u 1 plus C 2 u 2 and the f times C 1 u 1 plus C 2 u 2. This must satisfy the equation. So, the left hand side of the equation is this. Now, this we can break as because it is a linear one, we do know that the derivatives property, we can write it as C 1 times the a of a times del 2 u 1 over del x 2 plus b times del 2 u 1 over del x del t plus c times del 2 u 1 over del t 2 plus d times del u over del x plus e times del u 1 over del t plus f of u 1 and c 2 times similar terms for the u 2. So, that is a times del 2 u 2 over del x 2 plus b times del 2 u 2 over del x del t plus c times del 2 u 2 over del t 2 plus d times del 2 u 2 over del x plus e times del 2 u 2 over del t plus f of u 2. Since u 1 and u 2 both are solution, we had seen that this is equal to 0, that is satisfying the equation. Similarly, this is also equal to 0. So, what we are getting is C 1 times 0 plus C 2 times 0, that is 0. Thus, this u is also a solution of this differential equation. This is what we are saying is that if we do get two solution of a linear second order homogeneous equation, then their linear combination is again a solution to that homogeneous equation. Now, let us come to the solution of second order linear homogeneous partial differential equation, which can be solved as ordinary differential equation. Let us see what does it says. We will see it through one example. Find a solution u x y of partial differential equation del u over del x 2 minus u is equal to 0. This is not u 2, this is simply u. Solution. Here this equation is involving the derivative with respect to one variable only x. We are having del 2 u over del x 2 minus u. So, rather than treating it as a partial derivative, we can treat it as ordinary derivative, second order one. That says is I can change it to the d2u over dx2 minus u is equal to 0. Now, this is a second order linear differential equation, homogeneous one. We do know how to find out the solution using that characteristics we are getting is latent roots. As solution of this is a times, because it is lambda square minus 1 is equal to 0, that is lambda is equal to plus minus 1, we would get the general solution of the form a times e to the power x plus b times e to the power minus x. This is solution of this ordinary differential equation. Here what we are assuming that u is function of x only, but actually what we have been given a partial differential equation which says it is a function of two variables x and y. That says I should get my u as a function of x and y. In ordinary differential equation we have treated this a and b as general constants. Now, what I could do it here is, because they are the partial derivatives, I could say is that is a and b are some functions of y. That is, we could say the solution of this partial differential equation as a y of a of y e to the power x plus b y e to the power minus x. That is, rather than having this as a general constants, we are getting actually the solution in the form of two arbitrary functions, where these functions are function of y only. We are not involving any term of x over here. So, we have got the solution of this partial differential equation, general solution, where we are getting is this arbitrary functions are involved. Let us do one more example. Solve partial differential equation del 2 u over del x del y plus del u over del x is equal to 0. Now, let us see. In this equation we are having here the derivative with respect to both the variables, and here is the derivative with respect to the one variable. Now, if I treat this del u over del x as some function of x and y, then this del 2 u over del x del y, that I could write it as, we are assuming is that interchange of the variable is possible in the derivatives. So, I could write it as del by del y of del u over del x. That is, if I assume p as del u over del x, then this differential equation I can change to the ordinary differential equation as the derivative of p with respect to y plus p is equal to 0. Again, this is first order linear differential equation. To solve it with using the method of variable separable, we could get that dp by p is equal to minus dy, integrate on both the sides, we get that log p is equal to minus y plus c1. Now, this constant, as in the previous example we have taken, because here what we are taking it, this is the derivative with respect to y. So, whatever integrating we are getting is the constant, that now we have to assume that a function of x. So, we are assuming it as c1 of x. Now, take the both the sides the logarithmic out. So, we get p is equal to c x times e to the power minus y. This is the solution of this differential equation. Now, what is p? P is del u over del x. Now, since again it is involving the derivative with respect to one variable only, I can treat it as again as a single as ordinary differential equation with respect to one variable. The only thing is, when I would integrate it out, I will take the constant should be a function of the other variable y. So, this says is this is del u over del x is equal to C x e to the power minus y, integrate it with respect to x on both the sides. What we get is u is equal to C x e to the power minus y. So, e to the power minus y, that would be treated as constant, because when we are taking the partial derivative, the function involving y is only y would be constant. So, this is f x times e to the power minus y, and the constant we are treating as g of y, because we are integrating with respect to x. What is this f x? Actually, in this one we are having is this c x. So, we have to integrate this c x. So, f x is nothing but the integral of c x with respect to x. So, what we have got, the solution of this given partial differential equation as f x times e to the power minus y plus g y, where this my f and g are again any arbitrary functions. These are the differential equations which we have solved as ordinary differential equations, because the derivatives involved we can break it into as the derivative with respect to one variable only, and we can treat the equations as derivative involving the one variable only, and so we have treated it in this manner. Let us take it, as I said, is that the normal form is also making simplified solutions. So, let us just treat one more example. Solve the partial differential equation x times del 2 u over del x 2 plus 2 x square del 2 u over del x del t is equal to del u over del x minus 1. Now, you see I am not having this coefficients as constant only, we are having this coefficients are the function of x. So, this is a principally linear equation actually. Now, for solving it, we will first find out the type of this equation. Now, we are going to solve it using the canonical form, that is we will change it to the normal form and then we will try to solve with the method just now we had learned, that is changing the partial differential equation into ordinary differential equations. So, here the coefficient of del 2 u over del x 2 is x. So, a is x, b is 2 x square and c is 0. So, b square minus 4 a c would give me 4 times x to the power 4, because b square and 4 a c is 0, which would be positive for all x, because it is x to the power 4 even power. So, it will always be positive, that says this equation is hyperbolic for all x. So, the characteristics could be obtained by the b plus square root of b square minus 4 a c, that is square root of 4 times x to the power 4, that is 2 x square, and b is 2 x square. So, 2 x square plus minus 2 x square upon 2 a, that is 2 x. Now, when I will take this plus x, I would get 2 x plus 2 x square, that is 4 x square divided by 2 x, that is 2 x, or I would get with minus sign as 0. So, we have got the two characteristics. One is given by dt by dx is equal to 2 x, another is given by dt by dx is equal to 0. So, we will get the two characteristic curves. One is integrating dt by dx is equal to 2 x gives t is equal to x square plus c, another dt by dx is equal to 0, integrating it gives t is equal to c. So, now we will change it to the canonical form. For that we require the transformations based on this one. So, this transformation would introduce x square minus t and z is equal to t. Using this transformation again we will go, that is del v over del x as 2 x, del v over del t as minus 1, del z by del x as 0 and del z by del t as 1. So, now find out del u over del x using the chain rule, del u over del v over del x plus del u over del z over del x. We would get it as del u over del v, because the derivative with respect to x of del v, this is 2 x and here it is 0. So, we would get 2 x times del u over del v. So, the second derivative del 2 u over del x 2, we have got del upon del v, 2 x of del u over del v. Why this we have to integrate differentiate this with respect to x. So, we are differentiating it with respect to v and then del v over del x, then we are differentiating it with respect to z and then del z over del x. Now, this is actually we can treat it as a product of two functions, that is one function is 2 x, another function is this one. So, we are first taking the derivative of this function. So, this function has been kept as such, and then the derivative of this function with respect to x, that is 2, and this function is as such del u over del v. So, what we have got 4x square del 2 u over del v 2 plus 2 times del u over del v, that is just this part is 0. From here we would be getting is 2x, that is 4x square del 2 u over del v 2, and this part is as such. Then we go for del 2 u over del t del x. So, with respect to t we get it differentiated with respect to t. In the t, this 2x is taken as constant. So, we will not be having that term, and when we keep this del v over del t as minus 1 and del z over del t as 1, we do get is minus 2x del 2 u over del v 2 plus 2x times del 2 u over del v del z. So, the canonical form of this equation, because this equation is involving the derivatives del 2 u over del x 2 and del 2 u del x del t and del u over del x. So, I am just putting all these values over here, del 2 u over del x 2 multiplied with x. So, we are getting 4x cube del 2 u over del v 2 plus 2x del u over del v minus 4x cube then we get 2x square times del 2 u over del x del t. So, again minus 4x cube times del 2 u over del v 2 plus 4x cube times del 2 u over del v del z. Del u over del x we have got 2x times del u over del v and constant minus 1 as such. Now, simplify this one, we say is that is this derivative with respect to v, the second derivative, the coefficient here is 4x cube, the coefficient here is minus 4x cube, this has been cancelled it out. The terms involving del u over del v, that is the first derivative with respect to v, we see here is plus 2x, here is the right hand side is also plus 2x. So, we get it, this is also cancelled it out. The term which is being left is this one, the second derivative with respect this one, the second derivative with respect to both the variables v and z. So, we have got 4x cube del u over del 2 u over del v del z is equal to minus 1. Now, we are not talking in the terms of x and t, the transformation we have to use for v and z. So, we have to write x in the terms of v and z. So, if we do write it out, we do get is del 2 u over del v del z is equal to minus 1 upon 4 times v plus z to the power 3 by 2. Now, you see I am getting this left hand side as the second derivative with respect to v and z, and this right hand side is not involving any derivative. We are just getting the function which is involving v and z. Again we will try to solve it using this changing it to the ordinary differential equation. What we will do is, first we will treat say del u over del z as some function p and then integrate with respect to v and then go with the z or other way manner. So, let us see. First I have taken this integrated it with respect to z. That says is I would get del u over del v as half of v plus z to the power minus half plus a function of v, because we had integrated it with respect to z. So, the constant has to be a function of v. Now, again integrate it with respect to v, what I would get u as integration of this with respect to v half of v plus z to the power half plus integration of this with respect to v. So, rather than calling it let us call this small g v, then this would be capital G v, because this is not the same function, this would be integral of this function what you are getting here. So, let us make it as small g. So, then this is capital G v plus a constant with respect to v, that is a function of z. So, now what we have got? We have got the solution in the form of v and z. My original equation was in the form of x and t. So, let us transform back these variables v and z in the terms of x and t. What we would get? We do get u x t as my v you have got as x square plus t, something like that one. So, we do get is that half of v plus z to the power half, that is x plus the function z is t, so f of t, and v is x square minus t, so g of x square minus t. That is, I have got the solution u x t as x plus a function of t plus a function of x square minus t. If you do remember, this is what we have got our characteristic. One characteristic we have got as x square minus t, or t is equal to x square plus c, and another characteristic we have got t is equal to c. So, it is similar to that what we are getting in the first order equations, that is in the terms of characteristic we are getting is that argument of the functions, and the solution we are getting in the arbitrary functions. So, till now we have done the 3 examples. First 2 examples we have done simply, that is some equations which were of the nice form, and we could directly integrate them with respect to one variable or the other variable. Then we have seen a little bit general equation, which we said is we transformed it to the canonical form. Canonical form says is we have got our left hand side a simpler one, which is involving only, or which can be checked as with the homogeneous one, that is with the, where we could treat it as the functions with the v and z separately, and then we integrate it out. But in all these examples we had seen that we are getting solutions in the terms of arbitrary functions. So, how to determine this arbitrary functions? In the ordinary differential equations we have got the solution in the terms of arbitrary constants, and those arbitrary constants we have found it out using the side conditions, that is either initial conditions or the boundary conditions. So, here also for getting this form of this f and g, that is getting this arbitrary functions, we require the side conditions. So, we get the solution of this unknown functions f and g, general function f and g, if we use the side conditions. In ordinary differential equations also we had find it out that those side conditions which we called either initial conditions or boundary conditions, they are coming from the physical problems. So, here also they should come from the physical problem. So, before getting that what kind of these side conditions we should have, let us try to formulate a physical problem in the form of solving a partial differential equation. So, we would be modeling some physical problem. Here in this example I am taking the modeling as vibrating string, or we are here what we would get is modeling of a wave equation. So, what we want, derive the equation governing small transverse vibrations of an elastic string. What does it mean? It simply says is that suppose I do have an elastic string which is being fixed at the 2 ends, that is I do have one fixed is that is we are taking as the initial point, and then another end is being fixed at L. Now, this is a perfectly elastic string, that says is if I deform it, it will come back to the original formation with certain vibrations. So, we take this elastic string and we want to find it out, that is if I deflect it or if I pull it out sometime, then it will give the vibrations, and we want at a particular time t. So, what we are saying is this is my variable x, that is the vibration would be actually in this form and the deflection would be in this form. So, we want the solution x t, that is at a particular time t, at a particular point x, what will be the deflection, that is what u x t we would be interested to find it out if we had deflected it or deformed it. So, we are interested to find out the deflection in this elastic string. Now, to model it, as we know that we require little bit more assumptions, so that we could model first a simple equation which we could solve, and then we will go for the further ones. So, let us, for simplifying it or for modeling it, we require certain assumptions. What are those assumptions? Let us see the physical assumptions which we do require. First is that the mass of a string per unit length is constant and the string is perfectly elastic. What we are assuming is that the string is homogeneous and it is perfectly elastic, means it is coming back to the original position. The second is that tension caused by the stretching the string to fix end point is so large that the action of the gravitation force on a string can be neglected. That is what we are saying is, that is the tension which we have made it, that is because we had fixed it up to the other end. So, the tension which has been created, that is such a large, that is the gravitational force which is pulling it down, that is negligible. That means, this is totally governed by the tension only. The third assumption we are making is the string performs a small transverse motion in vertical plane only. That is, the when we are deflecting it and then we are leaving it, the motion which is being occurred, that is only in the vertical plane, that is this way the string is moving. It is the none of the time this horizontal motion is being done in the vibrating string. Let us see that is how to derive this differential equation for this. So, let us come back again to our model. This is the string which we have done. Let us take a small portion on this string, this PQ. So, correspondingly the points which we are having on the x axis is your x and x plus delta x. At this point, what we are having is, that is because it is governed by the tension only. So, we first find out what are the forces which are acting on this P and Q. The forces which would be acting on this P and Q would be the tensions, they would be in this form, and what we do have is, that is the tension would be totally because the motion is horizontal is vertical, the tension would be on the would be tangential to the curve of this string, that is at P this tension would be T1 and at Q the tension would be T2. And the now we will just see is, that is what will be its factors. So, we get is in the horizontal one, that is what we are assuming is, with the horizontal line this tension T1, that is this tangent is making the angle beta at the Q and angle alpha at P. What we are assuming that horizontal your part of this tension, this would be creating you, this should be the constant, because we are saying is that there is no horizontal motion. So, it should be constant. What it says is that this side this motion is this force is T cos alpha, here this force is T cos beta, that should be a constant. So, let us say T. Moreover, the vertical component of this T1 and T2, for T1 vertical component would be minus T1 sin alpha. Why minus sign? Because you see is that this tension is towards the downward side, and for this the vertical one would be T2 sin beta. These are the forces which are acting at these 2 points P and Q on this string. What would be the acceleration at which it is moving is, that acceleration we do know it should be the acceleration, because we are having only with the vertical plane, that means my velocity and acceleration both are with respect to t only. So, we do have acceleration, that is the second derivative of u with respect to t, that is del 2 u over del t 2. Moreover, we had assumed that the mass is homogeneous. So, let us say if that what is the string here we do have is, let us just call it delta x times. So, the mass is if constant mass rho. So, mass would be rho times delta x. So, now total forces which are acting on this string would be T2 sin beta minus T1 cos alpha, that is the vertical ones, T2 sin beta minus T1 sin alpha. Now, what we would use is we just model it using the Newton's second law, which says is that force is mass into acceleration. Just now what we had find it out, the acceleration we had find it out that it should be del 2 u over del T 2. Force we had find it out that is it is T 2 sin beta minus T 1 sin alpha. Acceleration and the mass we had find it out as rho del x. Now, if I keep it over here, what we are getting is T 2 sin beta minus T 1 sin alpha as rho times del x times del 2 u over del T 2. Now, divide this equation by a constant. So, the constant which I am going to take, that is the horizontal component of the tension T 1 and T 2 that we have taken as that to be the constant T. So, we just divide it by the T, this is what we have taken. So, divided by this T, what we do get T 2 sin beta over T minus T 1 sin beta over T is equal to 1 by T times rho delta x del 2 u over del T 2. Since T 1 cos alpha and T 2 sin beta, they are same as equal to the T. So, T here I am replacing by T 2 cos beta, at this place T I am replacing by T 1 cos alpha. What it says is this would give me tan beta, this will give me tan alpha, and what we are getting is tan beta minus tan alpha is equal to rho del x upon T times del 2 u over del T 2. Now, what are this tan alpha and tan beta? Let us again come to our figure. This alpha is the angle which this T 1 is making with horizontal one. So, what would be tan alpha? Tan alpha would be actually, and this tension is actually tangent at the point P. What it says is that tan alpha would be nothing but the slope of this string at the point P. Similarly, tan beta is nothing but the slope of this string at the point Q. Now, slope you do remember, that is we are finding it out because the string we are seeing is with respect to the variable t only, that is we would be getting is the slope is with respect to x. So, del u over del x, that is tan alpha is del u over del x at x is equal to p, and tan beta is del u over del x at x plus delta x or at x is equal to at point Q. That says is now it will transform this equation as del u over del x at p and del u over del x at, this is del u over del x at x plus delta x, this is del u over del x at x. Now, we will take here in this one itself that as q is approaching to the p, that is if I take this q is approaching to p, this delta x will approach to 0. Now, let us see that is this is an important part which the next slide I would be using. So, what we have got this equation now, if I write these in this form, that is tan beta minus tan alpha is equal to rho del x over t times del 2 u over del T 2. This can be written as del u over del x at x plus delta x minus del u over del x at x divided by delta x. This delta x I have taken this side, here it is rho by t times del 2 u over del T 2. Now, as delta x is approaching to the 0, what we do get, this is nothing but the second derivative of, or this is the derivative of del u over del x with respect to x again, that is the second partial derivative with respect to x. So, what we would be transforming, del 2 u over del x 2 is equal to rho by t times del 2 u over del T 2. Now, this rho is the mass, homogeneous mass, and T is that constant tension along the horizontal one, that also has to be positive. Actually, this both rho and T has to be positive. So, if I include this rho by T on this side, that says is T by rho, this has to be, this constant has to be positive. To make it sure that this is positive, we are introducing here the constant C square, because this is homogeneous mass and this is your constant tension. So, we are getting it a constant, but that constant has to be positive. So, make it sure that it is always positive, we are introducing this constant as C square. So, now what we have got, the differential equation which is governing the deflection at a time t with the point x at that point x is been governed by this differential equation, which is partial differential equation c square del 2 u over del x 2 is equal to del 2 u over del t 2. This equation we will recognize, this is nothing but our one dimensional wave equation. Now, we will learn it to how to solve this equation, but before solving we do know that till now whatever solutions we have got all them in the term of arbitrary functions, and to determine a unique solution we require side conditions, and those side conditions has to come from this physical problem only. So, let us first find out what are those side conditions which we could get in this physical problem. First thing is that we have took this string is being attached to the two endpoints at 0 and L. That says is we must get two boundary conditions, that is whatever be this function u x t, that should be here because it is being fixed up at these 2 points. So, it should be 0 over there, that says is two boundary conditions we are getting, that u at x is equal to 0 for any time t, u 0 t must be 0 and u L t must be 0, that is the deflection at those 2 points must be always 0. Then since the deflection is going to depend upon what is the initial velocity of the one, and since my time t is starting from any 0 point, that is we could say is initial conditions. So, we will get actually two initial conditions also for this problem. What are those two initial conditions? One is that what is the originally at time t is equal to 0, what is the form, what is the shape of the string, because by shape of the initial time, that is what is the shape of the string, the deflection will depend upon that. So, initially what is the shape of the string, let us say this is the form of f x, and how it would accelerate depending upon the initial velocity. Velocity means is the derivative with respect to t at initial point t is equal to 0, let us say this is g x. So, what we have got, we want to find out the deflection u x t in the vibrating string at any time t at any point x, which is being governed by this initial boundary value problem. That is, we have got now to solve this initial boundary value problem, which is involving the second order partial differential equation c square del 2 u over del x 2 is equal to del 2 u over del t 2 with boundary conditions u 0 t is equal to 0, u L at t is equal to 0, and two initial conditions that u x at 0 is f x and del u over del t at t is equal to 0 is g x. Let us see, that is to find out the solution of our physical problem, we have to solve this initial boundary value problem. Let us see how to solve this. First, we would use one method which is we are calling separation of variables. Here what we are meaning is, we are saying is that the function u, which is of the two variables x and t, that is that can be separated as a function of x and a function of t. So, we are also calling this as a product method, because what we are assuming is that u x t is the product of two functions, one function involving only x, another function involving only t. Now, if I am assuming like this one, then in this case when what we will get, actually our partial differential equation will change to two ordinary differential equations, and then we would be able to solve those two equations separately and put our side conditions over there to get the unique solution of that problem. How we are going to do it? Let us see. The two equations we will get, one is independent variable x and another is independent variable t. So, u x t is f x and g t, f x into g t. So, if I differentiate it with respect to x, we are having in our equation del 2 u over del x 2 and del 2 u over del t 2. So, if I am differentiating it twice with respect to x only, partial derivative with respect to x, that means the differentiation would affect only the part which is involving x, and this part which is involving only t, that will remain as a constant. So, what I would get is del 2 u over del x 2 as the derivative of second derivative of this f with respect to x. So, rather than writing it as a partial derivative, this could be treated as ordinary derivative with respect to x and gt. So, let us denote it by f double dash x, that is derivative with respect to x, second derivative with respect to x of the function f into gt. Similarly, if I take the partial derivative with respect to t of this function, that will affect only this function, but not this function will remain constant. So, I would get it f(x) into the second derivative of g with respect to t. So, either you write it partial derivative, or we can simply say is the derivative with respect to t. So, let us denote it the derivative with respect to t of g as g double dot. What we are just using the different notations, just to say that this dash when we are using, it means derivative with respect to x, when this dots we are using, it is the derivative with respect to t. Now, if I substitute these in our given equation, c square del 2 u over del x 2 plus del 2 u over del t 2, this what we would get, c square f double dash x g t is equal to f x g double dash t, it should be t. Now, since I am taking that u x t is f x into g t, and that should be a solution of this equation, that means this function f x into g t, this should satisfy this equation. That means it must be equal. It must be equal says is that left hand side is involving this x and this is involving x and t. Now, let us divide it by the whole equation by c square into f into g. What we are getting it here, f double dash x upon g x, because what we would be getting, c square is cancelled out with the c square, g t is been cancelled out with the g t. Similarly, here we would get g double dot t over c square g t. Now, if this is true, then this must be true. This side is involving only function of x, this side is involving only function of t. That is, whatever be this function, this has to involve only x terms, this has to involve only t terms. If it is satisfying this equation, they must be equal. How they could be equal? It simply says is that both these terms has to be a constant. So, let us say that constant to be k. Now, if I treat this, if take this as k, this has to be a constant k, then what I am getting is this equation is actually giving me two differential equations, ordinary differential equation. One equation from this first one, f double dash x is equal upon f x is equal to k, which gives me f double dash minus k f is equal to 0, and the second from here which gives me g double dot minus c square k g is equal to 0. You see, both these equations are linear, second order linear differential equation with constant coefficients and homogeneous right hand side is 0. We do know how to solve it. So, we will solve them one by one. Let us take the first this equation f double dash minus k f is equal to 0. This is second order linear differential equation with constant coefficients. We do know that its characteristic would be lambda square minus k is equal to, characteristic equation would be lambda square minus k is equal to 0. That said is okay. Before solving it, let us just move it to the side conditions, that is our boundary conditions. Let us see. If I do get g t is equal to 0, then my equation u x comma t is f x into g t, that will give me f into g as 0. We do know that we require non-trivial solution. So, 0 is a solution is not required, because this 0 is solution to both these equations. So, g t should not be 0. Similarly, the boundary condition when I do keep u at 0 t is 0. What it says is, since t cannot be gt cannot be 0. So, f x into gt is equal to 0 simply says this, f at 0 must be 0, because gt cannot be 0 for any of the values. So, f at 0 has to be 0. Similarly, f at L has to be 0. So, the two boundary conditions which we are having for our partial differential equation, in this method when I have taken this u x t as the product of two functions f x and g t, those boundary conditions has transformed to the boundary conditions for the first equation f double dash minus k f is equal to 0, with the boundary condition f at 0 is 0 and f at L is equal to 0. So, let us now see this first problem, that is boundary value problem for this equation. Similarly, if this boundary value problem, or if I am getting any solution which says is f has to be 0, that is also not interested solution, or that is also a trivial solution. So, we are not interested. Now, let us come to this one, this boundary value problem. So, this is second order linear differential equation, its characteristic equation is lambda square minus k is equal to 0. So, what we would be getting is, first with this constant k, either this constant k is 0 positive or negative. Let us treat them one by one. If my this constant k is 0, what will happen? I would get my equation f double dash is equal to 0. That says is, I would integrate it twice. So, I would get first f dash as constant, then say b a, and then we will get f as a x plus b. Now, if I try to satisfy these boundary condition, that is at x is equal to 0, if I put f 0 is 0, that says is I would get b is equal to 0, and at L I would get a L which is 0, that says is my a is 0 because L is not 0. That says is I will get this both the constants a and b as 0, which says is that f has to be identically 0 for all x. But this says is that I am getting u x t as 0, which is a trivial solution and we are not interested. So, this when k is equal to 0, this boundary value problem gives only trivial solution. We do remember that we require non-trivial solution. Now, let us come to the second case when k is positive. K is positive means we are having, let us say k as mu square, we are having the equation f double dash minus mu square f is equal to 0. So, the general solution in this form of equation is a times e to the power mu x plus b times e to the power minus mu x. Now, try to satisfy the boundary conditions. When at x is equal to 0, we get a plus b is equal to 0, and if at L is equal to 0 gives me, because a plus b is equal to 0. So, we get b as minus a. So, we would get a times e to the power L mu minus e to the power minus L mu is 0. Now, this function would be 0 if e to the power L mu is same as e to the power minus L mu. That would be same only when this both L mu is 0. L mu would be 0 if either L is 0 or mu is 0, but mu is not 0 because we have taken case to be positive, that is k is not 0. So, mu is not 0. Similarly, L is not 0, L is the other point where we had fixed it up, that says is I would get only trivial solution again, that is a is 0. So, we have got a is 0 and b is equal to 0, again we have got a trivial solution. So, this is also not of interest. Let us come to the third case when k is negative. Let us assume that k is equal to minus rho square. So, what my differential equation has transformed, f double dash plus rho square f is equal to 0. We do know the solution, general solution of this form of equation is a times cos rho x plus b times sin rho x. Now, we want to find out this a and b with the help of this boundary condition. At 0, if I keep, I get a is equal to 0 because this is 0 at x is equal to 0, this cos 0 is 1. So, I should get a is equal to 0. Now, if I put the other condition, that is f at L, I should get b sin rho L is equal to 0. Now, to get non-trivial solution, I must get this b to be non-zero. That says I must get sin rho L is equal to 0. That means, I should get rho L as n times pi, where n is any integer positive or negative, or we take that rho to be of the form of n pi over L. So, these are the only values for which I do have the solution of this boundary value problem involving the first equation f. So, what we have got the solution. Now, the solution I am writing f n x b times sin n pi x over L for n 1, 2, 3 and so on. This n can be negative, the only thing is with this negative, this b I could take this b to be negative. So, that is not of that much, we are not distinguishing it over here. Now, take the other equation. Other equation says is that the second derivative of g with respect to t minus c square k g is equal to 0. Since we have got that for k 0 and k positive, my f is coming out to be 0 only. So, those are not the case in which I am interested, or we are interested to get the solution. So, we will take the case when k is equal to negative or k is equal to minus rho square and rho is n pi over L or rho square is n pi over L square. That is the only case in which I want this solution of this second equation. If I keep this like this one, what it says is my equation would be g dot plus c square rho square g is equal to 0. Again this is linear equation, second order linear homogeneous equation. So, the solution of this, general solution of this is of the form a cos c n pi over L t plus a star times sin c n pi L over t, because rho is n pi over L and c is the constant over here. So, we are getting this as the solution. Now, we require this a and a star are here arbitrary constants. Let us write it again, because we are involving this n. So, we are writing d n t a n cos lambda n t plus a n star sin lambda n t. So, what we have got with lambda n I am writing as c n pi over L. So, the solution what we have got of our partial differential equation c square del 2 u over del x 2 is equal to del 2 u over del t 2 as u n x t as a n cos lambda n t plus a n star sin lambda n t times sin n pi x over L. This was b I have taken here as 1, some constant 1, let us say. Now, this is one solution of our equation, and this actually is varying for every n 1, 2, 3 and so on. It may be even the negative sign, again we have to take the b as the minus 1. So, we are getting the different solutions of the partial differential equation. In the very first lecture we had seen that is partial differential equation may not have single solution, we may have more than one function as the solution of partial differential equation. So, here we are getting as a lot many functions as the solution, where this they are varying with the n. What, let us see these solutions how they are looking like. This solution, this function u n x comma t, this we are calling eigen function or characteristic function for this initial boundary value problem. Actually, we have not solved this initial values, we have not satisfied the initial conditions, just this boundary value problems. And this lambda n, this is known as the characteristic value or the eigen value of this boundary value problem. And this lambda 1, lambda 2, this complete set is known as the spectrum. This u n x t is called the harmonic motion for each n. Let us see for fixed t, that is how with it is moving. So, the harmonic motion with the frequency lambda n upon 2 pi s c n upon 2 L, because lambda n is nothing but c n pi over L. So, if I just keep it out, it would be coming out n times c upon 2 L. So, let us see that is how it is looking. If n is equal to 1, this is the solution u x t. If n is equal to 2, the solution is this one. If n is equal to 3, you see that in the first one we have had only the strings, the same kind of function. Here the solution is like this one. We are having at the 2 point it is going down, here it is at the 4 point it is going down and so on. So, what we are getting this harmonic motion u n x t, we are saying is for different n values we call it nth normal mode of a string. for n is equal to 1 we do call it fundamental mode. Since sin n pi x over L would be 0 for all x as L by n to L by n so on. So, we do get that nth normal mode of the string will have n minus 1 nodes, that is what you had observed, that is when n is equal to 2 we have got, that is we are getting the uxt 0 at one point, then when it is 4 we are getting at 3 points. So, the first normal mode is known as the normal mode fundamental mode, and other modes are being called overtones, that is how many times they are going up and down. This is vibrating string, this is being seen in the all those instruments which are being played by string with the help of strings, and that is the term is coming as overtones and this ones. So, you could see is that this is a physical problem of that kind, but what we see is that is if I try to see this solution u n x t. So, here is that is for different values of t, if I take the second normal mode where I should get 1 point, that is 1 node, we are getting is that is as t is increasing to this decreasing to this side, my function is moving downwards, while from this side it would be, that is after the node it would be moving upwards. Let us see this initial conditions. At t is equal to 0, u x 0 is f x and initial velocity is g x. So, if I take the first one u 1 x t, a 1 cos c t pi over L, a 1 star sin c t pi over L, sin pi x over L. At t is equal to 0, if I put, I would get a 1 sin pi x over L as f x, and del u 1 over del t, I would get a 1 star c pi L over sin times sin pi x over L is equal to g x. Now, from here we do know that for x is equal to L upon pi, I would get it as 0. So, a 1 is I am getting as f x is equal to 0, or a 1 we are not getting the function, a 1 we could not be able to define. Similarly, here a 1 star I will not be able to define when my x is L, or you could say is L, 2L, 3L and so on. Similarly, if I go for the second one u 2 x 2, again if I put t is equal to 0, we would get a 2 sin 2 pi x over L is equal to f x, and the second initial condition would give me a 2 star c pi L over by L times sin 2 pi x over L of is equal to g x. Again we see these constants we would not be able to determine when x is equal to your L by 2 L, 3L by 2 or so on, neither this a 2 nor this a 2 star. So, what we have got? We have got the solution of boundary value problems, which are many solutions. We have got as u n x t as a n cos lambda n t plus a 1 star sin lambda n t times sin pi x over L. So, today we had learned how to model one physical problem into the partial differential equation, second order partial differential equation. Basically, we had modeled a first one dimensional wave equation, and we have modeled the side conditions, that is initial boundary value problem, that we tried to solve using the method of separation of variable, that is with the product method, and we have got many functions as a solution where we are not able to satisfy the initial conditions at that. Next we will see that is how to get the solution of complete initial boundary value problem. So, today it is over here. Thank you.